Okay, ma'am. So
you can start the session.
Yes.
Yeah.
So good afternoon
Yes.
to all of you.
Thank you.
I'm Dr. Sanjeev, and today I'm going to demonstrate how to start this Tanner EDA tool. It's a very, you can say the essential tool for the VLSI. Those who are already working on VLSI and those who are working, those who are thinking to work in VLSI. So you can opt this Tanner kits. There are so many things to learn in this Tanner. It depends upon you that what kind of circuit you are going to implement. So basically we'll start with the basics. So just so these are my outline of presentation. Is it visible?
The first slide only visible, the title slide.
Okay. So let me log in from this device. Then only it will work, I think.
Okay,
Yes,
sir.
yes.
Okay,
So
sir.
I'm leaving this one. So am I audible, ma'am?
Yes, sir. You are audible. Yes, sir.
And the slide is also visible.
Sir, you are audible. Sinha. Slide visible,
Okay.
but it's
Yes, ma'am.
we are able to see only first slide till.
Okay. Now the second slide is there. Online.
No, sir.
I think you have to share completely your computer.
Yes, sir.
Share complete.
Okay. Just good.
Share your computer, entire computer.
Some problems there.
Okay.
Some problems there. Just wait.
Yes, sir. Yes.
There is no share option.
Sir, Sinha sir ఉన్నారా? ఇందులో
Ma'am, I have
with
logged
what
off,
name?
logged
Sir, with
off second device. Give me
kind of
share.
logged in?
Yes, yes, I have logged in through only one device. Give me access for this device. Dr. Sanjeet K. Sinha.
Okay, sir. ఇచ్చారా? Sir, now the option, share option is given, sir.
No, ma'am, it is not visible. It is not. It is disabled.
Presenter option is given, sir. You could able to see here.
But share option is disabled. I don't know why this is disabled, but it is disabled.
Sir, log out from both the systems and systems of them.
Okay. Ma'am, share option is not there. Am I audible?
Yes, sir, you are audible, but we are able to see the option to your name. I don't know what's happening from that end, from this end, we are not getting. We are able to.
This is disabled.
Participants are also share options enabled only, ma'am.
Participants also?
I can also share my content here. The share options enabled for us
that's
also.
what. Yes, that's what we gave share option to everyone. That's what I mean. Previously we.
But I don't know why it is not coming to my side.
Like that is just enabled to our. Yeah.
From our side, we can see your shareable chart.
Okay, I'm just logged out once again.
Suggesting better you log out first, log in with only one system then.
Ma'am, am I audible? Just wait, I will send you the snapshot. Okay. Now it is now it is enabled. Are you
Join
getting my
and
voice?
yes, sir. We are getting voice and able to share now.
Yes, now it is enabled. Just wait.
Yeah. Very sorry, deep sorry to all the participants for the inconvenience causing here. Ask the participants, another participant is asking, should we open Tenor tool that is installed for working on it? So will they?
Yes, I
will they
will
do
give
parallelly with you? So some suggestions, please. Some suggestions,
yes.
please.
First I will share the slides. Just wait. I will give.
Yeah.
Now I'm sending you a image that you can see.
Okay.
Sharing option is not common. Why it is disabled?
Sir, otherwise, is it possible to share the PPT for us? So we'll
Yes,
run the PPT from our
yes,
from our end.
yes,
So you can.
I have just forwarded you. You just download and share.
Hello.
I have just forwarded you PPT.
Okay.
Yes, to your mail.
Fine, sir.
And you can see I have given one image that what kind of the sharing option, why it is disabled. You can see the WhatsApp image also.
Yes, sir. Yes, sir. Madam is downloading.
You can see the image on WhatsApp. Why it is disabled? The share option.
Okay.
Okay, otherwise you can share the PPT from your side.
Yes, sir. Madam is downloading. She will
Okay.
share.
But you can work on this one also. Why it is not appearing at my side? Share option.
Yes, sir. Yes.
System preferences.
Are you getting share option now, sir?
No. Have you seen the image? Why it is not there?
Yes. Yes, sir. We have seen WhatsApp video, WhatsApp image. Share option is not highlighted.
Yes, that is the main problem. Why it is not highlighted? I don't know.
You downloaded that WebEx, sir.
Yes. Everything is there. And we have already checked last day also. Day
Sir,
before day
are you
also.
presenter? Are you having the right of a presenter? Because it is saying that you should be a presenter, then only you would be able to share.
I don't know
So
whether I'm present.
the admin of the meeting should give you presenter right.
Yes, because it is
Yes, sir. We have given presenter option. But still, it's not getting that option.
still I'm having the same image.
Sir,
So
is the email ID same? The presenter ID given to the email ID and the ID that from which Sanjit sir have login. Is it same?
yes, login is all. Yes, same. Yes, I have entered the same login.
Sir, whoever is sharing and the screen now, they need to, I think, first stop the sharing, and then you would be able to perhaps share it.
Yes, sir. Yes, sir.
Yes.
Hmm.
So I'm leaving the meeting. Once again, I will join. Meanwhile, you can download the PPT. Are you getting my voice, Parvati ma'am? Parvati ma'am?
Yes, sir. You are audible, sir. Yes, we are able to hear you.
Okay, now you can share the slides. This is the only option. You can share.
Sir, is it visible to you? PP?
Yes, ma'am.
Yeah.
Yes, it is visible. You just changed. Is it changing? Yes, fine. Okay, so I will start from here. I think I don't know what is happening, which type of glitch we are facing, because we are dealing those glitch in VLSI simulation, and the same glitch we are facing today's presentation. So am I audible?
Yes.
Okay, fine. So,
Sir.
okay. So in this particular presentation, we'll discuss how to start this EDA tool, this tenor EDA. Then we'll go for the basic circuit, that is the inverter. So first we'll see, and if after some time, if everything becomes fine, then I will go for this inverter implementation in the tenor EDA tool. So first we'll start with inverter. Why inverter? Because this is the basics of VLSI. When you go for any circuit implementation, when you will go for any different technology also, rather than this MOS technology, when you will go for FinFET, TFET, CNTFET, then if we are talking about, since we are talking about the front end, the tenor, the circuit, so we are talking about the front end. So what we'll do, you can make your own device. For example, you can make a P-type P MOSFET, N MOSFET, and after having P MOSFET and N MOSFET, you can easily implement an inverter. So inverter is the first basic circuit of the VLSI. So that's why we will first see how to design this inverter, and if you have designed successfully this inverter, then you can design anything. So after inverter, I will tell you what are the things involved in buffer design, then what are the things involved in the universal logic gates. Here in CMOS logic, things are reverse. In general, in digital electronics and in you can say the when we talk about the VLSI, then in that we'll start with the basic gates and or, and since we have already discussed inverter. But when we talk about the CMOS logic, here we'll start with the universal logic, because CMOS itself says that it's complementary MOS. So we'll start with the complementary logic. So what are the complementary logics? NAND and NOR. So first we'll see how to go for this NAND and NOR. Then we'll go for the logic gates. Logic gates means we have already designed inverter. Then we'll go for AND gate and OR gate. After that, we'll slowly we'll go towards the circuits. So first we'll see the half adder, then we'll go for full adder, and after that we'll see what are the things associated in multiplexer design. And finally, we'll go for some sequence, since we have discussed lots of things about the combinational circuits like half adder, full adder, multiplexer. So we'll design a flip-flop also, so that once you have designed a single flip-flop, then you can design any register, any type of you can say the counters. So these are the outlines of the presentation. The next. Okay, so when we'll go for design these basic circuits in Tanner software, then we must have this Tanner software in your laptop. So this is the download link, and this link, through this link, you can have installation steps, because it's a little bit critical. If you skip a single step, you are not able to run the circuit, right? So everything is given in this link. You can follow all the steps, then you are able to run the simulation. So next one. So ma'am, have you given this link to all the participants, Parvati ma'am?
Yes, sir, I gave, and some of the participants have downloaded also.
Okay. If they have downloaded, then I will come to any one participant and I will demonstrate. Okay, next.
Yes, sir. Yes, sir.
Yes. So as we have discussed that if we are talking about any VLSI circuit, then we'll start with the CMOS logic. We must know the CMOS logic. What is CMOS? And as I told you that in VLSI, implementation is not a big task. If you know how to design, how to implement the circuit, then it is very easy to design the same thing in the any. I'm not talking about this is irrespective of any tool. Either you can use Cadence, Mentor Graphics, or any tool, any front end tool. if you know how to design the circuit, because for example, if you don't know how to design full adder, if you don't know how many inputs are there in full adder, then how you can design? So you must have a clear cut design idea, then only you can design those things in the any EDA or you can say the CAD tool. So if we are talking about VLSI, then we'll start with CMOS logic. CMOS logic, as we have already discussed, that the C stand for complementary. So basically, this is complementary metal oxide semiconductor. So whatever right now, whatever we are having technology, which is already followed by the semiconductor industry, that is the CMOS technology. In CMOS, we are having two types of network. The first one is pull-up network and second one is pull-down network. The upper, you can see in this image, the upper part is pull-up network and the lower part is, you can say, pull-down network. And one more thing is associated to these two networks, that pull-up network comprises always PMOS, whereas the pull-down network always have N type of MOSFET. We cannot change those things. And according to that principle, we will design our circuit. Okay, next. So this is the typical CMOS inverter. So in CMOS inverter, as we are going to design this inverter by CMOS logic, so we have to consider both the things, pull-up network as well as pull-down network. So in pull-up network, we are having a PMOS device, whereas in pull-down network, we are having one NMOS device. And if you will arrange those things in this way, then, and if you will apply a common input to both the gates of this PMOS as well as NMOS, then simply you will have an inverted output like this. This is the typical symbol of the inverter, and same thing we will get when we'll arrange our PMOS as well as NMOS in this way. So this is a typical CMOS inverter. So what is the inverter? When we'll apply 0, then we'll have 1, and when we'll apply 1, then we'll have 0. So basically in digital design, 0 means we are applying a 0 volt and 1 means we are applying the VDD, whatever we are giving the VDD. So let's say if it is 5 volt, then it is the 1 is your 5 volt, that is high, and the 0 is your low, that is 0. So it's very simple, 0 to 1 and 1 to 0. We are going to design the same kind of inverter in the Tanner circuit, Tanner tool. Next. Yes, so but before going to design this inverter in Tanner, we must understood the concept of this inverter, how this 0 becomes 1 and this how this 1 becomes 0. So you can see this is the typical structure of this inverter. So when we'll apply 0 at the common input, common gate of these two devices, so what will happen? Since upper one is your PMOS logic, lower one is NMOS logic. So when we'll have 0, then see this 0 becomes 1 at the pull-up network, and when it becomes 1, then whatever we are applying at VDD, that is reflected at output. So, and at the same time, when we'll apply 0, this NMOS becomes off because it need 1 to on this transistor. So in this case, only PMOS is in on condition, and NMOS is in off condition. So what will happen? If we'll apply 0, we are getting 1 at the output. And reverse kind of things will happen when we'll apply 1. Here, if we'll apply 1, this PMOS becomes off and this NMOS becomes 1. And once this NMOS becomes on, then this is grounded. So what will happen? Whatever we are applying here, everything becomes the grounded. So if we are applying 1, then we are getting 0. So this is the typical, and same thing we will observe in the waveform of this in this tool. Next. So now you can see This is the typical inverter which I have designed in Tanner. So what you will do, simply you can go to the S-edit. There are two things, S-edit and W-edit. In S-edit you have to design all the circuits, in W-edit you have to see the waveform. So here you can see this is the simple PMOS, this is the simple NMOS. I have connected this PMOS NMOS, I have given one input here, and I have connected this, you can say, the common gate of this PMOS as well as common gate of this, sorry, it's not common gate, common gate is connected to this input. Here we can connect this common part to the output. Now since we have to apply, since this is a logic design, so we have to apply a waveform. So I have applied a waveform here, and since this VDD, this is the symbol of VDD, so we have to apply 5 volt at this VDD. You can directly connect this 5 volt to that VDD. You can directly connect to this, you can say, the pulse, input pulse to this input port. Right. So for the better understanding, I have implemented separately. Now, what is the meaning of this? This whole circuit, this 5 volt is applied at this PMOS, and this pulse is applied at the input port. Now, based upon that, we'll go for the output. Can you change that? To see the output, you have to select this print voltage option. Since we are applying a voltage pulse at the input and we are observing a voltage pulse as in terms of output. So what we'll do, simply we will select this print voltage 2 times and we will attach at input side and we will attach at the output side. So that, what is the meaning of this print voltage? We are able to see the waveform at the input port as well as we can able to see the waveform at the output port. Once we'll attach this print voltage at input and output, and once again, once we'll go for the run button, then simply we will have the waveform. Can you change the next slide? Scroll up, down. Now you can see this is the typical inverter output which is observed from this circuit. Now you can see here, this is the upper one is your input signal and lower one is your output signal. When we'll apply 0, we are having 1. When we'll apply 1, we are having 0. 0, when we'll apply in the input, we'll get the 1. And when we'll have 1, we'll get the 0. These are very simple. And but if I have simulated those things, then it becomes fine. So anyone is having this particular tool in their any participant?
Yes, sir.
Who has gone?
Install the tool that you have seen.
No, your voice is not coming.
Yes, sir, we have installed the.
We have installed the tool that through the link that you have sent.
Okay, that 16 version.
Yes, sir.
Can you share so that Parvati ma'am, can you give the access to those? Let them share. I will instruct from this side, so that it's a kind of hands-on.
Yes, sir. I stopped my sharing so that the people who have loaded the tool can share their window.
Yes.
Yes. Any participant can come forward to show your to share your screen, so the tool can be explained.
Okay, ma'am, I would. You cannot share it.
Yeah, please. Sir, I think presenter. I should presenter. May I know the people? I mean, who is presenting and the name, please?
Ma'am,
Manoj.
can I
Manoj
share?
Sharma.
Yes.
I'm sending my Gmail ID, ma'am, so that you. I'm sending my Gmail ID so that you can give me the right.
The name itself we can give.
Madam, it is
This
Dr.
one, sir.
Manoj Sharma. Parvati ma'am, it is Dr. Manoj Sharma.
Yeah, yes, we are able to see his name. Yeah.
If anyone is able to share, then I will explain how to. Actually, still, ma'am, it is not share option is not there in second.
Sir, Manoj.
Yes, ma'am. I'm trying.
Yeah, yes, sir.
So, are you able to view my screen, the tool window?
Yes, sir.
Yes,
Sir,
it
Dr.
is
Sinha,
visible.
sir. Yeah.
Yes, fine. Very good. Okay, so how we will start? You have already installed Dr. Manoj.
Yes, sir.
Okay, now you can go to this file, click on file,
Yeah.
go for new design, click on new design. You can write anything. For example, we are going to, yes, inverter, yes, FDP, fine. Okay, now you create a folder anywhere in your desktop. You can select the path at any desktop. Have you followed all the steps of installation, Dr. Manoj?
Yes, sir. Yes, sir.
Okay, then it is fine. You can save it anywhere in desktop, no issue. You can select.
Sir, I need to take care of the memory. In the desktop I do not have.
Okay.
Just 1 minute, sir. This, or I can give over here. No problem.
Okay.
It is working slow.
Okay, no issue. So you just scroll down this command window below this screen. Below this screen.
Can I close it?
No, don't close. You just scroll down.
It is
Drag
saying
down to this screen.
okay.
Drag down to this screen. Drag it to down. Yes, leave it. Now you have gone through the file. Then go to the cell.
It is not. It is just still in processing, sir.
Okay, which one?
I do not know what happened. The system is working very slow all of a sudden.
Ma'am, can I share my screen?
May I know who is that?
Yes.
Akash?
Okay.
Okay. Let me stop.
Yes.
Yeah, I have stopped sharing.
And
Okay.
making presenter. Yeah. Akash.
Akash.
Mr. Akash. Yeah.
Akash Vayal.
No, ma'am. No questions.
Okay, ma'am.
Akash,
Now
sir.
I'm sharing. Yes.
Yeah, able to
Sir,
see the
is this?
yeah, we gave you.
Yes, sir.
Fine.
Okay, ma'am.
Yes, fine.
Sir.
It is visible.
Very good.
It is visible. So
Uh,
yes, I think you have implemented all the things. So are you able to
yes.
have the waveform?
No, sir.
Okay, so do one thing. We can start it from the beginning so that
Yes, sir.
everyone can understand, right? So
Okay,
what
sir.
you will do, you
Correct.
can start afresh. You can you just yes, it's just
You can
delete all
save your
those
work,
things.
sir. Right?
Okay.
You
So
can save your this file. You can save otherwise.
yes. It has saved. Yes. New design, sir. Right?
Yes, new design.
Yeah.
You can put some name. Yes. Then I think you have given some path. So click on OK. Okay. So what is the name you have given? Akash 1.
Sir, one.
Okay, inverter. Now you can go to this cell. Yes. Go for new cell, new view. Click on that. You just put some different name. Yes, cell 0, you can keep it. Otherwise, you can give some other name also. Keep it as cell 0, no issue. Go for OK. Okay. So just wait. Akash, since you have already done all those things, but someone has
Yes, sir.
not performed yet. So we'll start with this one. So first step is to go for this file, make a new file, then go to the cell, new view. After having this black kind of window in front of you, what you will do is just go for, in the beginning we have discussed that, okay, Akash, can you tell me which tanner you have installed? Is it 16? Whatever ma'am
Yes, sir.
has given?
16.3. Version
Okay, 16.
16.3.
Okay, 16.1. Okay, fine. So as we know that those who know this VLSI, so in VLSI, in every 18 to 24 months, technology is going to change. We have seen the, the later micrometer technology, then nanometer technology came, and now we are having 12 nanometer technology. Understood? So as this Moore's law suggested that every 18 to 24 months, this technology is going to change. So what is happening? This particular 16 version of this tanner is based upon 250 nanometer technology, right? So right now, I think the licensed version is 20 or more than that is available in the market. But since this is freely available, so it is useful for you. The almost the working principle is almost same. The difference is for the technology node. So what we'll do, first we'll go for the library addition. So how to add this library? So click on this add. Parvati ma'am, meanwhile, you can give me permission from another system. I'm trying. Yes.
Okay.
So have you, okay. Yes.
Sir, present be only one.
At a time.
So
Okay.
at
Okay.
a
No.
time only one. Yeah.
Okay. No issue. I will complete it. Okay. So click on this browser. The three dot. Yes. Click on that. Fine. So here you can go for this. Click on the generic. No, not this one. Go to this main. Yes. This set. Yes. Fine. So here you have to select this analog library, the upper one, the first one. Double click on that first one. Yes. Double click. Yes.
Yes.
Now you have to select this generic 250 nanometer analog library file. Click on that, and
Yes.
then you can open. Press on open. Now it is included. Press OK. Now it will be included in your left side. Now that technology file we have included. Now the second one is when you will design the circuit, then input and outputs are required. So what we'll do, we will include the library file of input and output ports also. So for that, once again, we'll go to the add, click on that add. Once again, click on that 3 points, go to the browser. Yes. This time, go back. This time we will go for, as we have discussed, we are going to have input and output ports. So we'll click on IO ports, the third one. Click on that, double click.
Yes, sir.
Yes. Now you can select this generic 250 IO pads. Okay. Open, then okay. Yes. Now you can say that your pre-production work is completed. Right. Now we are going to design inverter. So for that, what we'll do, simply we will go to the 250 nano, scroll down, 250 nanometer devices. Scroll down. Yes. From here, you can see when you will click this 250 nanometer devices, the NMOS and PMOS, different type of NMOS and PMOS are visible in this window. So you can select this PMOS because first we'll go for the pull-up network. So first we'll select this PMOS 2.5 volt. It is upon you that whatever you are going to select, either you can select 2.5 or 3.3, but you have to maintain the same similarity. If you have selected PMOS 2.5, then you have to select NMOS 2.5. So let's select this 2.5 volt. And one more thing, if you want to change, come to this instance, the lower window, this one, this side, the instance window. If you want to change the symbol, this side. No, in this small black screen.
So this
Side, in your left, small
this?
black, yes. So if you want to, now since we have selected this PMOS 2.5, so this symbol will appear in the screen. But if you want to change this, then there are so many options. Click on this cursor here, symbol, two arrows are there below that one. Symbol is written, two arrows are there. Yes, click that arrow continuously. You can able to see different type of structures are appearing, right? So go to the first one. Yes, this one. Go to it. No, not this one.
This one, sir.
Yeah, this one. And click on instance. Yes. And drag it here. Yes. Paste it here. Just leave it. So this is your, you can say PMOS. Right. Now you can zoom. Yes. Zoom out. Not, yes. Some little bit more so that we will have both the circuits. Do one thing, Akash, you just cut this command window. It will appear automatically. This command window is there, no? Some cross is there at the corner of this command window. Cross it. This command window, lower command window.
Door? Okay. Yes.
You cross it. Yes. Now it is bigger. Yes. Drag it to your left. Press Alt. First you press yes. When it becomes yellow, then press Alt and drag it to the left. Yes. Leave it. Don't go that side. Watch that. Okay. Now PMOS is, we have considered the PMOS. Now we'll go for NMOS. So once again we'll go to the same window, and this time we'll go for NMOS 2.5. Go to the instance, click on instance. Yes. Now you can drag it. Yes. Leave it. Okay, fine. Now PMOS, NMOS we have considered. Now what is the next objective? Our objective is to select VDD and the ground. So for VDD, you just go to the miscellaneous library. Go to the inverter, click on miscellaneous, MISC. Go to this VCC, VDD, the third from the bottom, VDD. Click on that, select this instance. Yes. Connect it to the PMOS. Yes. In the same library, you can select the ground. Okay, fine. Now what you will do, you can select this wire. Where is wire? Because your name is visible there, you just select wire from the
Okay.
top menu.
Yes, sir. I have selected it.
Because you know, your name is visible there, so it is not visible from there. So everyone, you can see, everyone can see this wire is after this particular yes, yes, okay. So now it was visible. Yes, now it is visible. Fine. Okay. So now you can select the wire. You can see this is the wire from where you can select the wire. Now you can go for full screen. Yes. Now from there you can connect this to. Yes, you can connect this to on. You can say the drain terminal. You can connect the gate. Okay, now go to select that input and output port that is also there beside this wire. No, no, don't go that side. Here only. Yes. Okay, no. Right side, right side. It is not visible. Yes. Do yes. It is fine. No, this side. Come to your right. Come to your right. More, more. Come to your right. Go, go, go. Next, next, next. This one. This one is your input, and after that, this one is the output. Select this input. Okay. Now connect it to the first one. Here you can select the east, west, so that it will move. Okay. Now you can press Alt. Press Alt. First you click on that. Press Alt and drag it. Connect it to this point. Oh, fine. Same way you can select the output from that menu. Okay. Leave it. Leave it. Don't, yes. Okay. So now it is out. Now this one is okay, but what we have discussed, we need to supply this VDD, because till now it is not specified whether this VDD is 3 volt or 5 volt or 10 volt, right? So what we'll do, once again we'll go to elements in library, go to the elements, second one, elements. Yes, spice elements. Here scroll down, you will have voltage sources. Click on the last one, voltage source. Now come to this instance. Since you are designing a digital circuit, so no, this is the AC. It is clearly written. We cannot consider this AC. We have to consider the DC. Go to the instance. Just press on done. Then it disappears. Done. Press. No, don't go for that one. It will be directly coming to the instance one. You just press done. This one, or you just cut this. Yes. Okay. Now go to the instance. Go to this symbol cursor. Symbol. Go to. Place your cursor to the symbol. Arrow. No.
No, sir. What?
Yeah, this one. The symbol cursor. Symbol is there, no? Press your cursor to symbol arrow.
Okay.
Down.
Yeah.
Down. Yes. Click on that one. You will have so many voltage sources. Click on that. Yes. First, everyone, you can see different kind of voltage are there. So according to your choice and requirement, you can consider, right? So what we have to consider? We have to consider a pulse signal. So click on that one. Next.
Yes, sir.
Click
This
next. One? No. Once again, you can press that arrow.
Okay.
More. Next. Yes, you can select this one.
Okay.
This is the continuous pulse signal. Otherwise, you can select a single pulse also. Now, click on instance. Okay, place it somewhere in the top of this corner, left corner, top left corner. Don't place it here, otherwise, yes, top left. Go to the top, drag to the top. Do not connect. Do not connect. I will tell you how to do. Yes,
Okay.
go to above. Leave it. Okay. Now this one is okay. Now you have to give this VDD also, right? Because still this one is for input pulse, and now you have to consider this VDD since we have selected this voltage source library option. So what we'll do simply, we'll check the VDD. Click on that symbol. No. In that elements only. Yes, click on that one. Click on that symbol. I will tell you which we have. We have to consider 5 volt, right? So press on that one. Press. Akash,
Hello.
press this. Yes.
Yeah.
Symbol. In symbol, you leave it that one. Your cursor is still in the main frame. Come out from that main frame. Go to the instance frame.
Sir, this.
Yes, and go to this
Okay.
symbol. No. Go to this symbol. Press your
Sorry.
cursor. Done. Press done. Okay, no problem. You can press delete. Leave it. That is okay. Once again, go to that symbol. Yes, here you can click on that arrow. We have seen different type of, yes. What kind of voltage we need? We need a fixed kind of voltage. Press next. Click on that. Yes, we need this voltage source. Select this one, go to the instance and drag it to the main frame. And yes, place somewhere at the right. Leave it. Okay. So once again, what we'll do, we need to define these two voltage. How we'll define? Once again, you can click on this VDD symbol. Click on that VDD symbol. VDD symbol, not that VDD symbol. Yes. Yes. Now once again, it is there in instance. Select instance. Go to the instance window. Yes. Click on instance. Yes. Drag it into the main frame. Come into the main. Don't go that side. Yes. Connect it there. Fine. Now go for this particular ground. Yes, you need 2 grounds, so don't okay, you have already deleted. So once again, you can select another ground and press it to that instance and drag it to this V1. Yes. Okay, fine. Now what you will do, once again, you can go and select this input port from this menu, bar menu, because the input is connected to this V1. Go to this bar menu, the upper, no, don't go that side, don't go that library side, upper window, where this from where you have selected this wire and input output. Go and select the input.
Just a second.
Yes, select the input port. No, yes,
From the menu,
towards
from the menu side,
yes, that
File.
that yes,
menu bar,
that
file menu bar.
yeah. Connect it to the V1. Yes, connect it to the V1. Drag to the V1, it will directly connect it. Okay, don't change anything, you just press OK. But where is your okay, now it is correct. Now your design is completed, right? Now what you will do, you have to give this, you have to see that waveform. For that, what you will do, you have to use those commands, print voltage. So for that, what we will do, we'll go to the library, select the commands, then print voltage. No, don't take anyone. You just go and select the print voltage. Press this symbol There are so many voltage, different type. Yes. Press this arrow. The lower arrow, you can press that arrow. You will have different voltage options. No, in that only. In instance window only. Go to the symbol. Yes.
Yeah.
Click on that. Yes. Press. Click on that one. Click. Next. 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 Yes, you have to select this print voltage.
Okay.
Go to select this instance. Click on instance.
Yes, sir.
Connect it to the input. Yes. Connect it. Yes. Anywhere you can connect. And another one you have to connect at the output. But I think what you will do, you just because otherwise all things are overlapping. So this one, second one, you have to connect at the output. How you will connect? Do one thing. Just put enter. Just put delete. Okay. Now you have connected. Fine.
So we can use R on the keyboard to rotate all these.
Yes. Okay, fine. Now it is, yes, you can use. Now it is okay. Yes. Now I think it is fine. Or otherwise you can use some wire so that your output becomes here and you can connect it this way. Now you just save this design. Click on save if you want to use those things. Now what you will do, you just go to this the third row. You can say no, what happened? First you go for the maximize, do the here. Where this tick mark is there, go for 1, 2, 3. This is the run setup. Go for the third one. First, second, third. No, before that. No. In third row only. Yes, before that. You just see. This is setup simulation. Click on that. Setup simulation. No, before that one. Before that one, setup simulation. The third one. Next.
This one.
Yes, click on that.
Participants, from your side, some noise is coming.
Okay, click on general. If you have installed all the things in right way, things will becomes fine. Otherwise, it will come some error. Now go here. When you will select this general, go to this library files. Library file is here. Click on that. Yes, go to that browser. Click on that. Okay. So now go back.
Participants.
Yes, sir. Yes,
Akash, click on this technology file, the last one.
technology.
File.
Okay.
Yes, the last one, tech file. Double click. Here you can select this generic 250 nanometer library. From yes, the next one. After that, the white one. Yes.
Okay.
File. Okay. Yes. Okay.
Okay. Should I open, sir?
Unmute. Sir.
Hello.
Sorry, actually I was muted.
Yeah. Okay.
Okay. So now you have selected this generic 250. Then press open. Yes. Now what you will do? Press your cursor in this link, whatever is there. Press your cursor in that link. Yes.
Okay.
And use your keyword, that arrow, and go towards your right.
Yes.
Yes. Good. Very good. Now you are at the last of this one, right? So press one space. Yes. Then type double T, capital double T. These two steps are necessary because without that you are not able to run the things. Now you just go for, just wait. You have press double T. Yes, it is visible. Now leave it. Go to this from simulation option. Go to the simulation output this side, second window, not in first.
Sir, this double T means typical.
Sir, third
yes.
one. This.
No. In simulation, outputs go to this one. Enable waveform voltage printing. It is false. You
Enable.
can press it to true. Press
Yeah.
on that false. Press
Yes,
on
sir,
false. Yes. Press. Click on that.
Yeah.
Now you can
True.
select true.
Okay. Yes.
But I think it hangs.
Sir. Are
Okay.
you
Now.
seeing? Yeah.
Okay. Now. Yes. Now it is okay. Go. Click on OK.
Okay. No analysis has been selected.
Okay. Just press OK. No. What happened? Once again, you just click on that simulation setup.
Okay. Yes.
Now you just check whether your library file is there or not. Everything is fine. Whatever we have, yes, that is fine.
Yes,
Now go
that's
to
fine, sir.
select, come to the left hand side, select the
Yeah.
transient analysis, the second one. Click on that. Yes. Now you can go for OK. Just wait.
Yes, sir.
Have you pressed OK? No. Now you just
No.
come to this stop time. Go to the stop time in the right hand side. Yes. Now here you have to type 100 nanosecond. Just any time you can give, right? So
100
that
and
ns nanosecond.
NS. Okay. Yeah.
Then maximum time step. Put 1 nanosecond. Then print start time. Press 0 nanosecond. Okay. Now you can press OK. Press OK.
Yes, sir.
Okay. Now go for run.
This
The
one,
next
sir.
button of this setup.
Start simulation.
Yes. No. Go for the run button. That is the fourth. Start simulation. Yes.
Start
Click on
simulation,
that.
right? Yeah.
Yes. Click on that, and if everything is fine, you will get the waveform. Click on that.
Yes, sir. I have clicked it. There is some delay. There is some lag. Yeah.
Okay. No problem. It will come.
Sir, it's
It will take some time. It will come. Just wait. No, fatal error.
fatal error.
Okay, go to the design.
Yes.
So this is the way to run the simulation. Go to the design. Just leave it. Go to the design. Yes, go to the S edit.
Yes, sir.
Here you can do one thing.
Bulks are not connected. Bulks are not connected.
Where?
They are connected.
I think
Sir,
that
body is not connected.
which body? Something is missing because of it is.
I think
NMOS and PMOS.
Kindly check library. Kindly check the library whether proper library been created or right. Fatal has some library.
Yes, because of that. Go to that one. I think here there is no such problem. Once again, you just go and check that
settings.
setup.
Settings.
Yes.
Setup.
Click on that.
Sir, yeah, generic 250.
Yes, Akash.
Yeah.
Click on that.
Yes, sir. Now.
But nothing is coming.
No, not the. No, not left side. That similar. There is setup, right? Earlier you did the setup where.
Yes.
No. Third row.
The third one.
Third row. Okay.
No.
Third. In third row, third option.
Left side. That one.
Yeah.
Yes.
Yeah. Setup simulation. Yeah. Okay.
Click on that.
Live you.
Once again, we'll see
The-
what they have
Yeah.
selected.
This is the library.
This library ensure that properly it is connected. That's supposed to be .lib file. It
Yes.
is not .lib. It's supposed to be the .lib.
Sir, so
Okay.
I think this is
Okay,
the file, I think. Because we have selected this XST.
No,
not that. It should be .lib.
Yeah, right.
Select the dot.
Okay.
From here, yes, you can select here.
There are several files actually that Control A, delete, freshly use.
Okay.
Yes, library file you can select from here only. If you will select the wrong file, it will not come.
This one,
But
right?
it is not
Now
visible.
open.
This one, right?
Yes, now open.
Yeah. Should I write the TT?
Now space there, capital T.
Yeah.
But nothing is there. It is everything is. Yes, now you can select this live file. Yes.
Okay. Okay.
Now click
Go to the
in
last.
the simulator.
Yeah. Okay.
No. Have you pressed that TT? Without that, it,
Yes, sir.
yes.
Yes, sir.
Yes,
Yes,
fine.
Yeah.
Okay.
I will start again, sir.
No, that's it. Now go for this. Yeah, start simulation.
Yeah.
If you will
Yes,
do
sir.
a single,
Yes, sir.
yes,
It
wrong
has
step,
come.
things will not come. Yes. What happened?
Yes, sir. It has come.
So go to the W edit.
Yes,
Yes,
sir.
fine. Very good. Now you just go and press that one so that you can split this waveform. Click on that.
Which one, sir?
That menu bar is there, no? So many. Okay. So once again, your name is coming.
Yeah, sir.
Yes, you just minimize. You just press this one. No. But it is not visible from my side. You can see there is a split option in above this one, the plus, minus, zoom.
Use right button, otherwise we'll get the option for that.
This. Yes. Press one split is there. Split icon is also there. Means yes. Once you will press that one, both the waveform get splitted.
Where is the split option, sir?
In that row only, but it is not visible. I can't see with the
Just a
exact
minute, sir.
symbol.
I'll check.
You can you zoom in a little bit so that I can see all the options?
Right click and extend traces.
Akash, can you zoom your video?
Or you can use
use magnify.
Extend traces. Right click and extend traces.
Just a minute.
Yes, you can go through in that way also. Otherwise, the simple icon is there. You just press. It will. What happened? What you have pressed? No, you have pressed.
Excuse me, sir. Towards your right hand side, I think. One blue color icon towards your right hand side.
No, it is not visible from that side. Okay, do one thing.
Blue color icon is there, no, sir? That one. Split window.
No, I think this
Right hand
one
side.
is.
No, sir. Right hand side. And one cursor link icon is there, no, sir? Towards that.
Yes, it is there.
Towards the left. Blue color icon. Next, left to that. Left of that one. The next one. That is split icon, actually. Yeah. It will be separating our windows. Yeah.
Yes, but I think you have zoomed. That's why it is not working. You just remember that
Yes,
one.
sir.
Otherwise, someone is saying that you just go to the right click and expand all. So many options are there, right? So, but you can't able to see. Once again, you just cross this one. Once again, we'll see the this window. You can cross it. W window, you can cross it. Yes. Go to the S edit. Once again, we can run.
Yes, sir.
Cross it. Do not save. Once again, you can run. because one waveform is you must analyze the one waveform so that you can go for the another one. Yes, now you understood where is that? Yes, got it. Now you can analyze. Now you cut this command window so that you will have a broader area. Close this command window.
Yes, sir.
Close it. Yes. Now you can see if everything is fine, all steps are in that way, then whatever we have explained. So you will have this kind of waveform. So Akash, now is it fine?
Yes, sir.
So now it is clearly visible that the upper one is the input, the lower one is the output.
Output, yeah.
Yes. So when you can see that when we'll have 1, then we are having 0. When we are having 0, then we are having 1. It's very simple. 0, 1, 1, 0, 0, 1, 1, 0. Understood? If anyone is having any doubt in this one, you can tell me. Once again, we'll discuss all those things. If you are having any doubt, anyone, any participant, this is very simple. Once you will follow all the steps, all the steps.
Sir, for this inverter, can we find out power dissipation or delay kind of analysis part? Do we do that?
Yes, you can do, but in this particular, this is free one, right, ma'am? So it is not possible. Sometimes we are having some, all the things are not available, but in license one, we can do for that one. Right? So in same way, but okay, so the 60% credit goes to the Akash Vyal, right, Akash?
Yes, sir.
For this simulation.
Yes, sir. Yes, sir. With of participants'
So
presentation as well as the tool supported mostly there.
Yes, and it is purely hands-on because they are doing the things by their own hand, right? Okay, so in same way you can design all those things. As I told you, if you will explore, all the things are available in YouTube. And as Parvati ma'am said, asked about the power and delay, these are also available with some crack version, the latest one, the 20 version. Those are a little bit complicated compared to this 16, but all the videos are available, right? And it is it needs some kind of revision. Means revision should be there. If you will revise those things, you will sit continuously on this particular 10, you can explore so many things, right? It is not possible to have all the things in 1 hour, right? So those who are interested, they can start with the 16 version, and if they wanted to do in higher technology version, then they can either they can manage to have the crack file of the latest technology, or they can ask to any you can say any researchers in ResearchGate or through ResearchGate, because they are helping, they are giving this latest technology file. Okay, now we'll come to the presentation. Ma'am, can you for the presentation so that I can
Mr. Akash, yeah.
Yes.
Will you
so after
share?
that,
Sir, one question here. Yeah, from my side, one sir.
Yes.
What are the libraries can be possible with this Tenor tool, sir? Like up to what technology?
Yes, because this one is whatever we are using, that technology, this technology is basically 250 nanometer technology. That is the quite older, or you can say no one is, because if you are talking about above 100 nanometer, then it is no more nanometer, right? And this one is 250 nanometer. But for the you can say for the starting your research, starting your circuit simulation, you can use this one. But if you will publish with this 250 nanometer technology parameters, no one is going to entertain. So for that, what I'm saying, you just go for the latest paper in ResearchGate. Those who have published the latest paper, you just contact to their author and you just request them to provide the technology file, latest technology file for example, 32 nanometer technology, 22, 12, whatever. And sometimes they are giving. If you will include those files, then you can able to simulate those things. Right?
Yes, sir. Yes, sir. So I can take back the presentation, sir.
Yes, yes. So I will completely, I will complete all those things quickly so that it is having a exposure kind of things. And although these slides are with you, ma'am, if somebody will ask you, just provide those slides to them.
Definitely, sir. Sure. Sure.
Yes.
Yeah.
So I will go quickly and just go for next one for buffer. Since we have already designed, as I told you, this is the simple basic steps that how you simulate those things and how you will analyze those waveforms, right? So since we have already demonstrated this CMOS inverter, sorry. So when we'll go for this buffer, then what is buffer? Buffer is simply combination of two inverter. So when we'll have these two inverter in this fashion, whatever is showing here, then you will simply have a buffer circuit. So next. Go for next. This is also the basic things. Go for the next one. Yes, you can see here. Since you have already designed the first part, the inverter, and when we'll have arrangement like this, and in the beginning I told you, when you will go for this particular EDA tool, then you must have the design tool. If you don't know how to connect, if you don't know where we have to connect those things, then you can't use this tool. So this is the typical design, and the same design if you will design in the Tanner, then you are able to have this kind of waveform, input and output. So you can go for next. So here you can see this buffer circuit where I have used two inverters, right? And you can see the same steps we have followed, that we have applied what is happening in buffer. We are applying 0, we are getting 0. We are applying 1, we are getting 1. The same input, the same output. So what we are doing, you can see only one input pulse is there, which is applied at the first inverter, and we are observing the output from the second inverter. So we have used this two print voltage. So two print voltage means we will get two waveform, the input and output. And when you will simulate this circuit, you will have the waveform in this way. You can go for next one. Yes. So this is the actual waveform when you will simulate this buffer. Simply here you can see when we'll apply 1, we are having 1. When we'll have 0, we'll have output in terms of 0. So that becomes a simple buffer. Go for next. In same way, you just go for the NAND gate. As we have discussed in the beginning that this CMOS logic is complementary logic. So first we'll try to simulate the NAND gate, NOR gate. And since these two are universal gate, and once we have demonstrated this NAND NOR, then you can design any circuit. So but you must know how to design this NAND. So how will design this NAND? In pull-up network, this PMOS comes in parallel. And in pull-down network, this NMOS comes in series. So this is the actual implementation of NAND gate, and you must know this one. Then only you can able to design in Tanner, right? Since this is a NAND gate, so you can verify your truth table through the waveform, right? Next. In same way, we'll go for the NOR gate. But things will change in NOR gate, because in NOR gate, we will have this PMOS in series and this NMOS are in parallel. And since this is NOR gate, so we required 2 inputs. So we are having 2 inputs, V1, V2, and we are getting the output. Next. So as I told you, must know the circuit. Then only you are able to design the circuits in the tenor. Now this is the typical. Yes. Someone is saying something?
Nothing, sir. You can continue. Yeah.
Okay. So this is the typical NAND gate implementation in this tenor, where you can see we have 2 MOSFET, 2 PMOS, and we are having 2 NMOS in series. These 2 PMOS are in parallel. So according to that design, as I told you, you must know the design. Then only you are able to draw those circuits. So here, what will happen? We are having 2 inputs and we are having 1 input. We just recall that table of 2 input NAND gate. So we have applied 2 pulses here, 2 inputs, input 1, input 2. And according to that design, that A, for example, if we are using A, B, then simply this is A, this is B, this is A, and this is B. The first upper one, the PMOS is having AB. You can see this 1 is A, this 2 is B, this 1 is A, and this 2 is B at NMOS side. And this particular VDD is coming in the same way, whatever we have considered for the inverter. And once you will simulate this particular NAND gate, then you will have the actual output. Go for next. Okay, and this one is typical NOR gate implementation where this PMOS, 2 PMOS comes in series and these 2 NMOS comes into the parallel. Since we are having 2 inputs, you can see. You can use, as we have discussed, when we are selecting that instance for those, you can say, voltage sources from elements, then you can select the different pulses here. So here it is, you can say fixed pulse. Yes, next. Now we'll see the waveform. Yes. So this is NAND gate output. You can see the first 2 is your input, the red one and the, you can say, the green one. Third one is your output. So you can see, you just recall the NAND gate. What will happen in 0, 0? We are getting 1. 0, 1, 1. When we'll have 1, 1, it becomes 0. This third, you can say, sequence. Whenever we are having 0, 1, we are getting 1. And once again, you can see whenever 1, 1, it becomes 0. So this is the actual NAND gate output. In same way, we'll go for the NOR gate output. So go for next. So here you can see, you can recall the truth table of NOR gate. When we'll select 1, 1, we are getting 0. When we'll select 0, 0, we are getting 1. So whenever 0, 0 is coming in these 2 inputs, we are getting 1. And whenever, and other than this, we are getting 0. 1, 1, 0, 0, 1, 0. It's very simple. Yes, next. Go for next. Yes. So since we have already designed, yes, the first before that one, previous slide. Yes. Now, if you are going to design a AND gate, then first you have to analyze how you are going to design AND. Since you have already designed this NAND and inverter, so NAND plus not. This is known as AND. So what we'll do, simply we'll design this NAND plus not. So in next slide, it is designed in that way. You can see. Here you can see this is the typical NAND gate implementation, and this is a simple inverter. Since this is also 2 input AND gate, so we have selected 2 input impulse, 2 input pulse signal, and only one output that is coming from this particular point. So in this, we have selected this 4 print voltage. 2 is for input, 1 is for NAND, and 1 is for AND. And when you will go for this particular waveform, then you can easily identify the truth table of this AND gate, 2 input AND gate. Go for next. So this is the typical CMOS AND gate. We have already seen this. These two are, first two are 2 inputs AB, third one is your NAND, and fourth one is AND. So whatever we are getting here, same thing is inverted in this AND. So this is the typical waveform of AND gate. Go for next. In same way, we'll go for OR gate. OR gate means NOR plus NOT. Go for the circuit. Here you can see this circuit is representing the first, you can say left hand side is representing the NOR and right hand side is your simply inverter. So when we'll simulate this one, we will get the OR gate waveform, which is illustrated in next slide. Go for next. Now you can see the waveform of OR gate. So it is almost similar way to design AND gate, right? Now we'll go for quite a complex circuit, that is half adder. So can you go for next one? Yes, and as I told you that before implementing the circuits on this scanner, you must know the design. So this is the typical half adder. I'm not going to discuss the half adder in details, but yes, in half adder we are having sum in terms of A XOR B. So it is like this. So, but if you will arrange in this way, it is still A XOR B, right? And carry is simply AB. So for carry, we are having a particular this AND gate, NAND plus inverter. But here what we'll do, you can see here A XOR B. This is a typical implementation of A XOR B, where A bar B. So these two are coming here, AB bar. And whatever is, as we have seen in AND and OR, whatever is series in pull up, those the same thing is parallel in pull down, and whatever is series in pull down, those becomes in parallel in your pull up network, right? So this is the typical implementation of half adder. Now if you will implement the same thing in tenor, you will get the half adder output. Go for next. Now you can see the typical implementation of half adder circuit. So what I did here, I have designed this one is A. So I have designed A to A bar, B to B bar. And according to A bar and B bar, you can see the circuit, somewhere A bar is required, somewhere B bar is required in this particular A XOR B. And this second one is typical AND gate implementation. Right. So if you will implement your circuit in that way, which we have discussed in the last slide, then surely we will get the output of half adder. Half adder means you are having 2 inputs and you are having 2 outputs. Means you have used this 4 print voltage option. 2 is for inputs, 2 inputs, and 2 print voltage is for sum and carry. Right? So next. Here you can see the first two are the inputs A, B, third one is your carry, fourth one is your sum. So what will happen in half adder? Half adder means when we'll have a different inputs, then we'll have the output. That is the concept of XOR gate. And when we'll have the same inputs, then we will have 0 output. Now you can see 0, 0. So at 0, 0 means we'll get the 0 output and there is no carry. 0, 1. Then we'll get the 1 output and there is no carry. When we'll have 1, 0, in this case also we are getting 1 as output and there is no carry. But you can see in this fourth P, that 1, 1, if we are having this 1, 1, then we are getting 0 as a sum, and in that case we are having carry. So this is the simple, justification. Through that you can justify that your circuit is 100% right. Okay. If you will implement something different, or if you will miss some part, then you won't able to have the outputs. Now this one is quite complex. This is full adder using CMOS logic. So what is full adder? Full adder is having 3 inputs, and obviously since this is the adder, so it will have 2 outputs, sum and carry. Now you can see this is the typical design of full adder by using CMOS logic. So that's why I'm saying you must know the design part, then only you can design those things in Tanner. Right. So from this part we are getting the carry, and from this part we are getting the sum. Now you can see we have started from the inverter. The simple 2 MOSFETs are there. Now you can calculate, you can count how many numbers of transistors are present in this full adder. Right. So now you can think this is the simple full adder. If you will go for the 4-bit full adder, then what will happen? Number of transistors is going to be increased. So later on, this is not, I have not discussed those things. You can use those things as a block, and you can call those blocks. For example, you can use a half adder. You can call that, you can save those as a block. You can call those blocks 2 times in a full adder. And if you are going for 4-bit full adder implementation, then you can design this full adder by using 2 half adders, and you can design 4-bit full adders by using 4 full adder modules. And this is the way, hierarchy wise. Otherwise it is not possible to accommodate all the transistors in a small window, right? But this full adder is possible to design in same window, so we have designed those things. So next one, go for next. So this is the typical design of this full adder circuit. In same way we have designed, which we have started in the inverter. If you are having that design with you, then you can implement as it is in this Tanner without any fault. And if you will implement, then you will have the actual results in terms of waveform. Right? So how many inputs are there in this full adder? We are having simply 3 inputs, A, B, C. And we are having 2 outputs, sum and carry. So you can see we have considered this 3 as this 3 print voltage. It is a smaller one, but it is visible for 3 inputs, and these 2, the right hand side, is considered for the 2 output, sum and carry.
Sir, a small question.
Yes, yes,
From
yes, ma'am.
a small question. As
ma'am.
the number of transistors are increasing, the design also clumsy. Do we have an option of creating a symbol? Symbol in
Yes,
the
yes,
sense
that's
like
what,
once we create half adder, we can make it as a
that's
symbol
why,
and
yes,
yeah.
I discussed those things, ma'am. It is there in that Tanner tool. Actually, what you will do, if, for example, if you are going to design a 4-bit adder, right? Then what will happen? We can design a simple half adder. We can make as a model. You can save it in the library. You just call that model 2 times for full adder. And if you are going for 4-bit full adder, then you just call that model 4 times. All options are there. These options are there. Otherwise, it is very tough to have 4-bit full adder in small window, right? It is there. Yes, next. And if everything is fine, then you are able to have this output. Scroll up.
Voice is breaking.
Okay, now it is fine.
Hello?
Is it fine? Is it fine, ma'am?
Yes.
Is it okay? Okay, fine. So this is the typical, you can say, whatever we have discussed, full adder, A, B, C, and this is the sum and this is the carry. You can analyze those things whenever 1, 0, 1. In that case, we are having 1, 0, 1. In this case, we are having carry as 1 and sum as 0. In same way, if you will go for the truth table, then this you can say waveform is justifying all the truth table entry, starting from 0, 0, 0 to 1, 1, 1. Yes. So after that, we have seen all those things. But since yes, this is quite interesting. 4:1 multiplexer. This is the typical 4:1 multiplexer. And if you are going to design, then it will take, so many AND gates. You can see 4 3-input AND gates, 2 NOT gate, and 1 4-input OR gate. But if you will design these things by using transmission gate, and generally people are preferring multiplexer by using transmission gate. A transmission gate is simply combination of NMOS and PMOS, and it is easier to design. So if you will go for the transmission gate implementation of multiplexer, then it requires minimum number of transistors compared to implementing by using these basic gates. You can see we are having 4 3-input AND gates, 2 NOT gate, and 1 4-input OR gate. So it is quite complex. That's why we will use this 4:1 multiplexer. We will implement this multiplexer by using transmission gate. So we just go for next. No, go for next one. This is the second slide. Scroll down. Yes, next one. So this is the typical 4:1 multiplexer circuit by using transmission gate. Here you can see only 6 transmission gates are required to implement this 4:1 multiplexer. Basically, in transmission gate, this one is the upper one is your upper one is considered as the NMOS, lower one is PMOS, NMOS, PMOS, NMOS, PMOS. In same way, if you will implement this particular design, then you will have the actual 4:1 multiplexer output. Go for the circuit. Yes. So this is the typical implementation of this particular 4:1 multiplexer. So what will happen in 4:1 multiplexer? We are having 4 inputs. We are having 2 select lines, And these two select lines are, for example, there are 4 options in this select line: 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. So we need two inverter kind of operation with that select lines. That's why in that design 2 NOT gates are there, right? So what we'll have, simply we are having 4 inputs, we are having 2 select lines, those are also considered as the input, and we are having 1 output. So how many waveforms we will have? 4 inputs, 2 select lines, and 1 output. So total 7 waveform will be there in this 4:1 multiplexer output. Total 7 waveforms. So you will be able to see all those 7 waveforms in the next slide. Go for next. Now you can see here all these 7. So A, B, C, D is your 4 inputs. This S0, S1 is your select lines, and this one is your actual output. So you can see clearly, based upon this select line, we are having outputs whatever is available at the input. Now you can see when we select 0, 0, what will happen? 0, 0 means we are selecting the A input at the output. So A is 1 here, so it is reflecting at the output. So it is still 1. Now you can see in this case where we are getting 0 output. So in this case we have selected, you just see when we are getting this 0. In that case we can verify whether it is correct or not. In this case the select lines are 0 and 1. 0, 1 means we will go for the second input. What is second input here? Second input is B. So B is 0 here, the same input is reflected at the output. In that way you can verify and it is 100% right. Because it won't give the wrong waveform if everything is fine. Okay, next one. Now the D flip-flop. Actually, till now we have discussed about the combinational circuit. So when we'll talk about the sequential circuit, then we'll have the flip-flops. You can say the flip-flops are considered as the basic building block of sequential circuit. And in general, we are using D and T frequently for the register and the counters. So that's why I have considered this D flip-flop. What is D flip-flop? If we are going to implement, since we have started through this CMOS logic, since we have started with this inverter, then first we know how to implement D flip-flop by using this NAND gate. So if you will, other than this NOT gate, if you will see, then simply this is JK flip-flop, where this J and K are sorted by this inverter. So inverter is between J and K. Now it becomes D. Why we have considered this one? Because it is widely used in the sequential circuit, D-type flip-flop. That's why I have considered this D flip. So this is the typical structure. Now you can see 1, 2, 3, 4. 4 out of these 4 NAND gate, 2 NAND gates are 3 input configuration, 2 NAND gates are 2 input configuration, and there is 1 inverter. So if you will implement all those things, you are able to have this D flip-flop output. So go for the next. Yes, so this is the typical implementation of that D flip-flop circuit. Right? So you can see this is the first 3 input NAND gate. 3 PMOS are in parallel, 3 NMOS are in series, and this is the another 3 input NAND gate, 3 PMOS, 3 NMOS. And this is typical 2 input NAND gate, this is 2 input NAND gate. And according to that connection, you just connect all the wires. And here, if you will connect all the things, then simply you will get the output. Right? So go for the output. These are quite complex, but if you will do sincerely, everything you will get. Yes, now you can see here. The upper one is clock. This is D. This is third one. This is the Q. This is the QR. Third one is QR. This is Q. So basically our main output is this fourth one. Right? Q. Q bar is simply the inversion of Q bar. Q. So you can see, as we know that the output of flip-flop depends upon the clock signal. Whatever is clock signal, we will get the output accordingly. Now you can see in clock, there are having positive edge clock and negative edge clock. So this one is positive edge clock. So what it means, whenever we are having a positive edge, the output becomes changed. Now you can see, this is output. Sorry, the lower one is output. This D is your input. In this positive clock, input is 0. So what we are getting? We are getting 0 input. But in same positive clock, this input changes. You can see the second pulse of this input, D. At the same positive clock, this input is changes to 1. At that time, this output becomes 1. Because this output is changing from 0 to 1. Now it becomes 1. But after that, since this clock is negative clock, it is no more at positive. So what will happen? This transition will not change, whether irrespective of input. Input is 0, 1, but it is still maintain the last stage. Right? Whenever it will have, you can see the third pulse of this clock. Whenever it will have the positive clock, at that time, according to that input signal, the D signal, it will change. Now you can see at this clock pulse, this D, nature of this D signal becomes 0, so it becomes 0. At the same time, at this clock, positive clock, this becomes D becomes 1 and it will change to 1. But it will remain 1 until it will have the positive clock. Clear? So this is the logic behind this one. So it is the waveform of D flip-flop. So that is the this presentation. And if you want to design, then you can go for
Hello,
counter.
sir.
Hello. Yes, ma'am. Counter and registers
hello.
also. Yes, ma'am. Tell me.
I think the presentation is done with this last slide, sir. Nothing.
Yes, ma'am. Yes, it is over. So go for the last slide. Last slide is simply.
Okay. Previous one.
Yes, ma'am.
Previous.
Yes. So now it is in this presentation.
Yeah.
So any question related to this one? If you will try in that way, you won't able to find any kind of error or any kind of difficulty while simulating in Tanner, right?
So sir, if the presentation is over, so we can, I think no more slides, sir. The last one,
slide.
right? Okay.
Yes,
okay. Yeah, stop sharing. Any questions?
Yes.
Participants?
This is the
in the
yes, ma'am.
sir, like consumption 1%, and power dissipation from other person. Darsana is one, Ravi is another person. Like there's some questions.
Yes, as I told you. Yes, I think you have asked the same question, Parvati ma'am, that how to calculate this power and area. As I told you, when you will go for the licensed one, then
yes, sir.
you can able to calculate those.
Yes, yes.
Yes, yes, and all the videos are available. How to go for that?
So yeah, with lot of patience, the participants have done this session.
Yes.
And glitches have come, but because of the glitches, we have able to see the participants' involvement in this. I hope completely.
In that way,
the participants we have seen the inputs and all. So I think the participants have gone with the inputs. So thank you so much for kind cooperation and excellent session, hands-on session. Though the glitches are there, we could able to complete this, and finally we have and make us participants to understand well about the tool and in this session itself.
Yes, ma'am.
So thank you so much.
Okay. Thank you. Okay, ma'am. So can I?
Thank you. Participants,
Yes, sir.
thank you for listening patiently.
Ma'am, I have a doubt.
Yes, you can ask.
Yes, so if
Regarding
if I
participants,
have a 45 nanometer
tomorrow we'll
library,
start.
If I have a 45
Sir, one
nanometer
question,
library, yeah.
Sanjit sir, Raju, yeah, there.
Yes, someone is asking.
Please carry on.
Yeah, if I have a 45 nanometer library and
Yes.
can I use that library in 16.3, this version?
No, sir.
Okay.
No, you cannot use 45 nanometer in this one because this particular 16 version is for 250 nanometer only. That's why I told you, you just go for the latest one, that is 20, 10 or 20 version. In that, they have used the latest one.
Okay. And sir, how to change the frequency of that signals, right? We are selecting that A and B signal.
Yes.
How we are changing the frequency? Because if they have same, then we will not get that right 0001.
Yes.
So how we are doing that?
Applying the clock, cycle will be different. I think the clock cycle should be different.
Yes, cycle will, you can, for example, if you are having 3 inputs A, B, C, then you just change their cycles.
On cycle and time duration we change. Yes.
Okay, in tool we have that.
Yes. The options are available.
Okay, thank you. Yes.
Yes.
Excuse me, sir. Ma'am, one more question can I ask?
Yes.
Yes,
yes, please. Yes, please.
Is it possible to design a FinFET circuits in Tanner, or only CMOS circuits we can able to do?
No, ma'am, you can use. That's why I told you, but it is a fusion of back end and front end. So what you will do that you have to develop a GUI code for that FinFET.
Okay.
In your TCAD or in your any visual TCAD or in your Centauros TCAD, and you can you can import that file into this Tanner.
Okay, sir. Can I use Verilog for that, or specifically Centauros TCAD only I am supposed to use?
No. Here Verilog, there is no use of Verilog. You can go for TCAD. TCAD, that is Synopsys TCAD or Visual TCAD. In that, you have to design a MOSFET, a single MOSFET, P-type and N-type, by using FinFET technology. FinFET technology or CNT-FET technology or T-FET technology, right? And you have to make their GUI. And you have to export those things, and in this Tanner you can import those things. So you have to use 2 tools at a time simultaneously, backend tool as well as front end. So in backend tool you are able to develop a PMOS and NMOS by using your FinFET technology. And once you will import those things in Tanner, then whatever you will design in Tanner, those things are based upon your TFET based MOS, and means TFET type and MOS whatever you have designed by using TFET technology. Understood? N type T4 TFET, P type TFET.
Okay, sir. In this version, sir, it is possible to export that.
No. In this version, it is not possible.
Okay.
Because this one is older one. It is freely available, and 250 nanometer no one is working on right now.
Okay, sir.
So if you will go for the licensed one, then you will have in our lab we are having the licensed one, where we are having only 45 nanometer we are having in our lab.
Okay, sir. Okay. Thank you so much.
Yes.
Any other questions from participants?
Good evening, ma'am. This is Dr. Ravi. Shall I ask one doubt?
Yes, sir. You can.
Sir, good evening, sir. Your
yes, please. Yes,
hands-on training is very nice, and also you explained very nicely for the Tanner tool. Sir, I'm having one doubt because I'm working in Synopsys, HSpace tool. So in that, if you want to measure the delay, we can go for a separate tool like Osmoscope. Like that, if there is any separate tool is available in Tanner to measure the delay, or directly we can measure in the schematic itself, sir?
No, I think in the latest version, you can do all the things in the same one. That's why I told you in this, they will not support, this tool will not, but in the latest, whatever we are having, everything is embedded there. So you can go for the power analysis, you can go for the delay, because when you will go for VLSI circuit, then these two parameters you must have to, optimize the power and area. But in latest one, the 20 or higher version, these things are available.
Okay, sir. Thank you.
Yes. Any doubt?
Any more participants?
Yes.
So, very nice session, sir. And the people participants enjoy circuits and all very hands-on, and people are putting the questions in the chat also. How to, like, some people, some participants are getting issues related and all. So I asked them to down once again.
That's right.
Using the
Yes,
whatever
there are two
provided.
links. Yes, two links I have already provided. You can go through all the steps, minutely. Don't skip a single step. If you will skip a single step, you will have some fatal error. You will have some different kind of errors. Yes.
So thank you for cooperation, and even participants also cooperated very well. Thank you. And I think we can conclude the session, and so tomorrow by 9:30, second session. See you all. Thank you all.
Okay, ma'am. Okay, thank you. Thank you, everyone. Thank you all the participants for their for your patience, because these are happening in online mode. These are the, you can say, the disadvantage of online mode. But I think some students, some participants have already, that Akash has already installed those things. So it is, we have used that.
Though it is a disadvantage, but it has become an advantage for us to see the hands-on really from their side really. Yeah.
Yes. Okay. Thank you all of you. It was a nice session. Okay, ma'am.
Thank you.
Excuse me, sir.
Sir, one more participant. Yeah.
Ma'am, please, we are new to this channel tool, ma'am. So can we have designing steps? Can we have the designing steps?
Yeah, we'll share all the material.
Yes, you can share all those things.
We'll share the PPT material, everything, no problem at all.
Yes.
Okay. Thank you. Thank you.
I think Sari is on live. You can.
Okay. Okay.
Okay, then participants will end for today. Yeah. Tomorrow by sharply 9:30 will be, because of inauguration we have started today 9 o'clock, and by 9:30 tomorrow we'll start. Thank you.